The conservation laws by starting in on the law of conservation of energy. And we're going to start with our first topic here, work and energy. This is going to be the only other topic we're going to take for this week because it's a short week. And we'll kind of go from there. All right, ladies and gentlemen. What is work? Work is something you guys should be doing. That's a joke. We usually think about the job, but our definition of physics is a little bit different. We're going to be talking about the amount of force applied over a distance. So this is, in physics, this is how we define it. First of all, work is a transfer of energy. Okay? Simplest definition possible. So for example, it could be you are imparting energy to a car when you're pushing it out of a ditch. You could be running up some stairs and you trip and fall back down the stairs. Okay? We are transferring chemical potential energy in our muscles into kinetic energy when we moved, and gravitational potential energy is being moved higher up. That gravitational potential energy could be moved to kinetic energy when you trip and fall back down the stairs. So we have a formula that we use. This is called the work energy equivalence, or work energy theorem, and that's the work is the change in energy. Okay? Very important. Now, also, work happens when a force causes an object to move through a displacement. Now, this makes some people say, hey, if you're applying a force, it means you're doing work. No, you're not. For example, get up right now, walk over the nearest wall, push on it. Are you applying a force? Yes. Has the wall moved? Gosh, I hope not. So, just because you apply a force does not mean that work is happening. So the object actually has a displacement, otherwise work has not happened. And here's the kicker. They must point in the exact same direction. Okay, so let's take a look. I want you to pause this and take a look. Okay, so I'm holding a 2-kilogram block of cheese in my hands and I walk. So let's try this. Here you are. You're holding a block of cheese and you are walking 12 meters this way. Did you do any work? Well, are you applying a force to the cheese? Well, yes, you are. Because, if you look at the cheese, just show a little quick free body diagram, cheese has gravity, and you are applying a force in this direction. However, what's the direction of the motion? Well, the direction of the motion is this way. Are you applying a force in that direction? Well, are you accelerating? Well, the question didn't say you're accelerating, so I'm going to say, no, you didn't, which means no force, which means no work. All right. Now, let's say you have a pet frog and you want him to get a little weightlifting because you want him to get all buffed, maybe make him into a battle toad, and you want him to start off slow. So he's going to start by lifting 10 kilograms up from the floor over his head and putting it back down on the floor. Did he do any work? Well, let's take a look. If this is the 10 kilogram weight, there's your force of gravity, and there's the force that's applied on the way up anyway. Is he doing work? Well, yes. It's going up over his head. That's where work is being done. How about here? He stopped really applying force, didn't he? And it's just all force of gravity. Is the frog doing work? No. The Earth is. Because the Earth is applying that force of gravity, that force at a distance. Picky point perhaps, but that is true. Now, also what you can think about this way, if you look at the whole thing, it travels up and travels down. Is work being done totally in the system? Well, no, because my displacement is equal to 0. He started off back where it began. There we go. So let's take a look here. Pause this one and give it a thought. All right, so there's a car. And we push the car, so we're applying a force this way. and it gets pushed out of the snow because it ends up traveling this direction. Is force being done? Yes. Okay, let's take a look. Please pause and take a read. Okay, so the book is going to travel down to the floor. The book weighs 10 kilograms, which means there's a force of gravity roughly 100 newtons. Okay, who's applying that force? Well, gravity. Did you do any work? Did I do any work? No. But the Earth did. Because the Earth is applying that force of gravity again. Okay, so let's take a look at this in a little bit more mathematical sense here. I want you guys to take a read through here. So these are the formulas that we are going to be using. You've already seen this top one, and this is an application of that second definition, this one right here. The force times the distance times the cosine, the angle between the force and displacement vectors. Okay, now what does this mean? Well, so this basically mathematically explains to us why it is possible for work to be done when vectors of the force and displacement are not parallel. So for example, if I'm pushing at 30 degrees, if I'm pushing a car at 30 degrees, if I'm applying a force 30 degrees from the surface of the car and the car goes forward, I am still doing work, but it's not the most efficient. So, and that's because mathematically there should be a horizontal component to my force and a vertical, and the horizontal component of my force would be in the same direction. So this also is why absolutely no work is done when it's perpendicular. So for example, if I'm holding that block of cheese, I am applying a force to the cheese, but it is 90 degrees to the direction of the motion, and the cosine of 90 degrees is 0. Okay. So if we look at this part right here, oh, sorry, this is just breaking it down into its components again, as we talked about. Okay, so by definition, let's take a little bit more definition of work and energy here, because we haven't done energy since we did heat in Physical Science 20. The unit for energy and work is the joule. You might remember that one. The joule is basically the 1 joule of work is when you apply 1 newton of force to an object for 1 meter. A little bit different definition. Work is no direction, so it's scalar. Okay, so we're not going to, but we can have negative work. Think of it. If I'm slowing down a car, I'm applying a force opposite the direction it's traveling. That means I'm 180 degrees. Cosine of 180 is -1. So that will make my work negative. So let's do this in an example. I want you to pause this video and give this a read. Okay, so these are my 2 kids. David decided he was going to grab Micah by his leg and drag him 2.3 meters across the floor. So if he exerted a force of 8.1 newtons to do this, how much work did he do? Well, work is equal to FD cosine theta. Cool. Well, that's pretty straightforward. One thing that might be tricky is the actual degrees. So here's the force applied, and he was dragging his brother in this direction. So that means that my angle should be 0. Which means that the cosine of the angle will be 1. Perfect. So now I just need my distance and my force. So he applied 19 joules of energy. Okay? Now, let's take a look at an example here. We're pulling a rope. So I want you to pause and read this actually, and then we'll do up a diagram. Okay, there's my box, and there's my rope, And this is 30 degrees from the ground. I guess I could have drawn it from down at the bottom, but I didn't. And I'm going, well, the box moves 12, it's going to travel 12.7 meters after 76 Newton force was applied at 30 degrees. So, using the same formula, we want to know how much work. Okay, force was 76.0. My distance was 12.7. And then I got cosine of 30. You punch all that in, you should get 836 joules. And there we go. And we are done this for today. So do your practice. There is also the answer key is included. And when you're done that, by all means, take a crack at the assignment. As per usual, please, you could either submit it as you have before. Just try and make sure that you tell me that it is the week 5 assignment, just in case I get confused. All right. Good luck. Hope to hear from you soon. And have a good weekend. We'll see you next week.